Okay, welcome back. This is Mr. Hassan's Maths channel, and this is question number 3 from Solomon K C4 collection, and this is also question number 5 from my P4 end of topic worksheet on partial fractions. And part A of this question tells us to express this function f of x in partial fractions. Okay, so we got to take this fraction and split it apart into separate parts, basically. Take it apart. Express it in partial fractions. That's what that kind of means, you could say. Now, in order to do this, what I've got to do is I can see I've got some factors in the denominator. One of them is a linear factor. The other one is a repeated linear factor. So the first thing I check for is it an improper fraction or a proper fraction? Now the numerator is of order 2, quadratic. The denominator, if you expanded it fully, you would get a cubic, so it's order 3. Therefore, it's a proper fraction. So I don't have to worry about any whole number parts. I just have to worry about these linear factors. So the first one is not a problem. It's a divided by 1 minus 2x. Now the second one, there's a repeated factor. So I have to write it in the following form. I write a constant over the factor when it's not repeated, plus another constant over the factor when it is repeated. That's how it breaks up a repeated factor. Now, if this was an improper fraction, then I would have to put a whole number separate part, at the beginning, which would be of order of the difference between the orders of the numerator and the denominator, but we don't have to worry about that in this question. We can just continue from here. Okay, so now what I'm going to do is I'm going to multiply throughout by the LCM of the denominators of both sides, which is 1 minus 2x times 1 plus x squared. If I multiply the whole of this side by that, I'll be just left with the numerator, which is 7 plus 3x plus 2x squared. And if I multiply this term by these, this product here, the 1 minus 2x will cancel, leaving me with 1 plus x squared. And if I multiply this term by all of this, one of the 1 plus x's will cancel, so I'll have b times 1 minus 2x times 1 of the 1 plus x's. And if I multiply the last term c by these two, then the 1 plus x squared will cancel, leaving you with c times 1 minus 2x. Now what I've got done by doing that, I've got rid of the fractions, and I can now look at how to deal with solving this problem. So there's a couple of ways we could solve it. One way we could solve it is by comparing the coefficients of x squared and x and constants. Another way we could do it is by substituting some values in to help us. Now I can see if I substitute x equals minus 1 into this whole expression, or cancel out this term and this term, because this will be a times 0 squared, and this will be b times something times 0, and you will only be left with the c term. Okay, so here what I can do is if I put x equals minus 1 into the whole thing, I have 7 plus 3 times minus 1, which is minus 3, plus 2 times minus 1 squared, which is plus 1, so 2 times 1, which is 2, is equal to, this will disappear, I'll be left with c times 1 minus 2 times minus 1, which is plus 2. Okay, so that gives me 7 minus 3, which is 4, plus 2, which is 6. 6 equals 3c, therefore c is equal to 2. So that's the value of c. And if I want to find the values of a and b, I could substitute a half into here, and this will cancel with that. They will both cancel, but that's going to be a bit of a hassle. I can think of an easier way if I compare the coefficients, for example, of x squareds. So on the left hand side, the x squared term is 2. On the right hand side, because it's identical, it has to be the same number of x squareds. And if you look at this and you expanded this will give you ax squared. And if you look at this term and you expanded it, you'll have b times minus 2x times x, which is minus 2bx squared. So I don't really have to write the x squared here because I'm just writing the coefficient. So this is a minus 2b. There will be no other x squared terms. So that's one equation I've got. And if I compare, for example, the constants, that's the easiest. They're normally the highest and the lowest is the easiest to compare. On this side I got 7. On this side I've got a times 1 squared, which is a, and I have b times 1 times b times 1 times 1, which is also plus b. And then I've got c times 1, which is c. So a plus b plus c is equal to 7. Now I know c equals 2. So I can say that 7 minus 2 is a plus b. So I can say a plus b is equal to 5. So now I have a pair of equations. I have a minus 2b equals 2. And I have a plus b equals 5. I can use simultaneous equations to solve this. If I subtract upwards, a's disappear. B minus minus 2b is 3b. And 5 minus 2 is 3. Therefore, b is equal to 1. And I know that a plus b equals 5. So a plus 1 equals 5. Therefore, a equals 4. So I know that a equals 4, b equals 1, and c equals 2. So now I can fill in these spaces. So I can say that 7 plus 3x plus 2x squared divided by 1 minus 2x times 1 plus x squared is equal to 4 over 1 minus 2x plus 1 over 1 plus x plus 2 over 1 plus x squared. Okay, that's what we wrote it. You have a over 1 minus 2x. Okay. What's going on? Plus 1 over 1 plus x plus 2 over 1 plus x squared. That's what this equals. Now to part B. Now part B says, show that the integral of f of x between the limits of 1 and 2 is equal to p minus ln q, where p is rational and q is an integer. So now, what we can do here is we can, this is exactly what we got when we split it up. This is a form which we are able to integrate very easily. We can't integrate this very easily, so we've got it right in the right form for us to integrate. So what we have to do is find the integral between the limits of 1 and 2 of 4 over 1 minus 2x plus 1 over 1 plus x. Now this, these two I can integrate using the ln function, because it's like the integral of 1 over x with respect to x gives you the ln of the modulus of x, which I'll explain in a little while. So it gives you this form. So if the denominator, if you differentiate the denominator and you get something of the same form, the same order in the numerator, then we can use this form here. So the differential of 1 minus 2x is a constant. It's minus 2. The numerator is a constant. That's fine. The differential of 1 over 1 plus x is 1. 1 is a constant, and the numerator is a constant. It's actually 1 itself. But the last fraction is not like that. If I differentiate this, I'm going to get like something, a quadratic in there. And the numerator is not of that form. So I have to write this as 2 times 1 plus x to the power of minus 2. And then I will be able to integrate this using a slightly different method of reversing the chain rule. Because what's outside, what's multiplying it, is the differential of what's inside, or of the same order of it at least. Now what I can do is I can integrate. So when I integrate this, this is going to be 4 times the ln of, you have to write the modulus, very important, 1 minus 2x. I'm going to explain at the end of why. Over the differential of what's inside the function, which is minus 2. So I write 4 times the ln of what's inside here, then I divide by the differential of what's inside the function, plus, and here I'm going to write the ln of the modulus of 1 plus x divided by the differential of what's inside the function, which is 1, so you don't have to bother. And here you're going to increase the power by 1. So it's 1 plus x to the power of minus 1. Minus 2 add 1 is minus 1. Divided by the new power, which is minus 1. And also divided by the differential of what's inside the function, which is actually 1. So it doesn't change that. And that has to be integrated between the limits of 1 and 2. Now, let's just simplify this. This is going to give us minus 2 times the ln of the modulus of 1 minus 2x. And this will be plus the ln of the modulus of 1 plus x. And this will be minus 2 times, or minus 2 over 1 plus x to the power of 1. And all of that with the limits of 2 and 1. Okay, what I could do here is I could try to make it a bit simpler. or I can just substitute the values in. I'm going to just substitute the values in now. All right, just substitute the values of 2 and 1 in and see what we get. So you have minus 2 times the ln of the modulus of, you're going to have 1 minus 2 times 2, which is 1 minus 4, plus the ln of 1 plus 3, 1 plus 2, which is the modulus of 3, minus 2 over 1 plus 2, which is 3, minus, and then I've got to put 1 in there. So I have minus 2 times the ln of the modulus of 1 minus 2, which is minus 1, plus the ln of the modulus of 1 plus 1, which is 2, okay, minus 2 over 1 plus 1, which is 2, and now I need to simplify all of that. Now this gives me minus 2 times the ln of the modulus of minus 3, plus, now this is positive, I don't have to write modulus anymore, ln of 3, that's fine, minus 2/3, then I've got minus and a minus, which is plus 2 times the ln of the modulus of minus 1, which is like the ln of 1. Okay, the ln of the modulus of minus 1 is the ln of 1, plus this is the ln of 2 minus 1. Okay, so sorry, let me start that again. You're going to have minus and minus is plus 2 ln of 1. The modulus of minus 1 is 1. And then you got minus and a minus, which is minus ln 2. And the minus and another minus will give you plus 2 over 2, which is 1. So now we got to simplify all of this. Now the ln of minus 3 is equal to the ln of 3. So this is minus 2 times the ln of 3 plus the ln of 3. And this is going to give you 1 minus 2. In fact, 2 ln 1 is 0, because ln of 1 is 0. So you end up with minus ln 2. And I'm going to have minus 2/3 plus 1, which is 1/3 plus 1/3. Okay, now these two can be simplified, because you've got minus 2 ln 3 plus ln 3, which is minus ln 3. And you've got minus ln 2 and plus 1/3. And we're kind of almost there. The answer, they said, in the form p minus ln q. Okay, so this is going to be 1/3 minus ln 3 minus ln 2. What I can do here is I can put this inside a bracket here, ln 3, and that's going to become plus ln 2, right? And those combine to give me ln 6. So I have 1/3 minus ln, I use a power law, ln 6. And that's the answer to the question in the form they require, where it says p is rational and q is an integer. P is rational and q is an integer. So you can say p is 1/3 and q is equal to 6. Okay, so there's the answer to the question. Now I'm going to digress a little bit here, because a lot of students don't understand why, when we integrate 1 over x with respect to x, we write the ln of the modulus of x. Okay, and I want to explain why, so that you will understand. Okay, so I'm going to go off the topic a little bit here. So I know that when I take ln x, if I say y equals ln of x, and I find the differential of ln of x, it's going to be 1 over x. Now when I write ln of x, there's a condition. There's a condition that exists, that x must be greater than 0, because the ln of x is a curve, okay, which does not exist when x is less than 0. It's undefined. It's like the reciprocal of e to the power of x. Remember, e to the power of x doesn't go below the x-axis. Ln of x doesn't go beyond the y-axis in the negative side. Okay. Now, if I have y equals a ln of minus x, and I differentiate the ln of minus x, to differentiate that, I have to do 1 over whatever's inside that ln, which is minus x, multiplied by the differential of what's inside there, which is minus 1, which also gives us 1 over x. So you can see that when I differentiate ln x, I get 1 over x. When I differentiate ln of minus x, I get 1 over x, exactly the same answer. Okay. However, there's a condition to this. The condition to this is x must be less than 0, because if x is more than 0, this will be a negative value, and you have the ln of a negative value, which will be undefined. So here in this case, the x has to be a negative value. Like if x is minus 1, that will be ln of minus 1, which will be, give you a value 0. Or if x is minus 3, that will be the ln of minus 2, which will be ln of 3, which will give us a value But if x is positive, this will be undefined now. And you can also think about this in terms of the curve. This is a reflection of the graph y equals ln x in the y-axis. So you can see it only exists when x is less than 0. That's another way you could think about it. Now, the issue arises is when we integrate 1 over x with respect to x. You can see that there's two roots that we can go back to. So 1 over x with respect to x could integrate to be ln of x. Okay, but that's only when x is greater than 0. And 1 over x with respect to x could integrate to give us the ln of negative x, but that's only when x is less than 0. Okay, so we know that the modulus of x basically tells us, its magnitude, how far away it is from 0 on the number line. Okay, so the magnitude of x tells us how far away it is from 0 on the number line. So if x is a positive value, then the modulus of x is x. If x is a negative value, then the modulus of x is the positive value of that. So if x is negative, then this is going to be like, this is going to end up as a positive value. So this together means basically the ln of the modulus of x. So that's why we write the ln of the modulus of x when we integrate a function. We write it as the ln of the modulus of x. Not because we say, it can't be a negative value in here, so we're just going to change it to a positive value. No. When something integrates into from 1 over x, if x is positive, it becomes ln of x. If x was negative, it becomes the ln of minus x, which means you're going to have to find the modulus of whatever you find. If it's negative, it's going to become a positive value when you put it in here. Okay, so that's the reason why we use ln of the modulus of x. So that answers this question, which is on partial fractions. If you would like to see other questions from this paper when I get around to doing them, you'll find them in this playlist that should appear over here. In this playlist, you will find other questions from partial fractions of P4. In this playlist, you'll find questions from this end of topic worksheet that this is from my end of topic worksheets on partial fractions. You can click on this link to subscribe to the channel, and on the top here you can find a link that will take you to another paper, paper 4, P4, that I have answered. Thank you for watching and see you soon.